We'll now continue with impedance analysis of piezoelectric and ultrasonic transducers, session number 3. I'll now go over the outline for session 3. I'll first describe how to calculate the equivalent circuit of a piezo resonator. So we have our capacitor in parallel with a LCR circuit representing the electromechanical resonance, and we have the parallel capacitor then describing the intrinsic capacitance or the static capacitance of the piezo element. Next, we'll describe summary parameters. That is to provide generalized parameters to describe the electromechanical response of your piezo as measured from the impedance analysis. It includes the equivalent circuit, but it also provides a more general framework by which to compare ultrasonic devices, both between different types of devices, and perhaps more importantly for practical purposes when you're comparing between devices that are supposed to be the same. We'll then talk about distributed system resonance. We spoke about this in detail in session 2, but here we're going to provide examples, at least two specific examples in FEA for ultrasonic transducers, describing how those their distributed system resonance then dictates their impedance response, and how that is also in turn affects higher order harmonics, which are a very distinct aspect of distributed system resonance. We'll then describe the differences between piezo crystal analysis and transducer analysis. So basically, piezo crystal analysis and using its impedance response is used to calculate material properties, whereas transducer analysis is done in a more general format, and material properties cannot be calculated and similar equations cannot be used. Piezo crystal analysis uses more complex equations, but that's because we try to isolate material properties from their transducer electromechanical response. In this slide, I'm going to go over the equivalent circuit calculations, and I'm going to be talking about the broader view of this. So when we do measure the impedance response of a piezoelectric resonator, and we specify a specific resonant mode, from your impedance analyzer you'll get an impedance response as well as phase. So here we'll have negative 90 and positive 90. So we'll also have phase, which around the resonant frequency we'll have this curve. So let's say a resonance that's about 0, and anti-resonance, again, we have about 0 degrees, and between resonance and anti-resonance the phase is 90. And before resonance and after anti-resonance we have a phase of negative 90 as the device behaves like a capacitor. Now we have a couple of so we have our equivalent circuit. And we have multiple unknowns. We have 1, 2, 3, 4, 4 unknown components. And in order to obviously isolate and determine the values for all of these components, we're going to need 4 unique measurements. But all of these measurements are not going to be necessary to do at different frequencies. So we're going to be needing 4 unique measurements, not all necessary at the different frequencies. So the first very important frequency that we're going to be using is the resonance frequency. So the resonant frequency of this, and this is going to be determined by this circuit, and specifically where the inductor and capacitor for this branch are at resonance. Now this frequency, so contrary to a common understanding, it's not the frequency of minimum admittance, although that is very close to the actual resonant frequency. What you will find that this is the frequency of resonance is the frequency of maximum power dissipation in this circuit. So if we have the maximum power dissipation, which basically means there is no impedance, this inductor or capacitor are in resonance, therefore they're not providing any opposition to current flow, and thus all of the current draw will be completed over the resistor, thus causing maximum power dissipation. This is actually the frequency of maximum real admittance. And if you remember admittance as being the current over the voltage, and in this case it's going to be cosine of the angle between them, which would be it's opposite to that of impedance, but for cosine, since it's symmetric, the phase angle doesn't really matter when you're doing those calculations. So basically the maximum power dissipation is the frequency at which the real admittance is the highest, so the real component being the dissipation of power. You could also, at that same time, if you wanted to do it in a different way, you could just you could get your voltage times your current amplitude. Let's do this in RMS, and you multiply that by the cosine of the phase, and you find where this is maximum. But not only where that is maximum, because, for example, if you have a voltage, a real amplifier, because actual amplifiers and actual driving devices are, the voltage supplied to your device under test is affected by the impedance of your device that you're trying to drive. So we'd like to normalize this to make it something like a transfer function. So if you divide, then in that case you'd want to divide by voltage, because that's being considered as the driver. So if you divide both sides by voltage, and this is equal to power, didn't write that earlier, but voltage times current times the cosine of the phase between them, and the phase is here. If you do that would equal power. So if you divide both of this by power, so voltage to power ratio, it ends up being the same thing as calculating the real admittance. So again, the real admittance is going to be what we're going to look for, and that signifies the resonant frequency. It's also related to power dissipation, which is a more readily understood concept, but not just power, but power per voltage, because the voltage for a test instrument, even an impedance analyzer, or if it's a high voltage amplifier, those do change as a result of the load, and they're not always predictable and linear. So in general, we look at admittance as a generalized way of looking at voltage input, current output. But if we look at the real admittance, it's going to be correlated to power dissipation. This doesn't occur. The same relationship can't be used. You can't look for the minimum real impedance. The reason is due to functions of complex math, and why the power maximum is not going to relate to the real impedance maximum. So I'm going to leave that topic there, but just know that this the real admittance relates to dissipated power, and that's how we define our resonant frequency. We'll now measure the impedance response of a ultrasonic transmitter and we'll be using that for the example going forward. So I have my frequency set from 35 kilohertz to 45 kilohertz, and I'll use a frequency step size of let's say 10 hertz using a series resistor for the current measurement of 100 ohms. Now if you're using a commercial impedance analyzer, that's not going to be a relevant parameter. Let's go ahead and assign the correct file name. So Sonic transmitter, basically the 40 kilohertz ones, which are very widely available. Let's go ahead and do that measurement. As we see in blue, the impedance reaching the resonant frequency at the minimum impedance, but as I mentioned, that minimum point here is not precisely the resonant frequency. The resonant frequency is actually going to be slightly higher, which is determined by the maximum real admittance or the maximum power dissipation. So here's that result, and we'll have that magnified there. So here we have the resonant frequency and the anti-resonant frequency. As we kind of see, they're not exactly aligning on the maximum maximum impedance and minimum impedance here. So at the resonant frequency, the frequency of maximum impedance, so we're going to plot, maximum admittance, real admittance, which is power. This is now the maximum real admittance. And if we plot real impedance, we have its maximum occurring at the anti-resonant frequency. If we just look at the real impedance or the real admittance, it's going to be sensitive to the resonant frequency, at the frequency at which we have the LCR circuit in true resonance. But if you look at the real impedance, it's going to be most sensitive to the anti-resonant frequency. And again, if just for kind of comparison, if we draw, if we write impedance for the second axis, looking at the minimum points, it doesn't exactly match up, and that's because there is that parallel capacitor which is drawing the apparent resonant frequency as measured by absolute impedance down. So the real impedance is only measuring, or the real admittance is only measuring the response of the LCR circuit, because that's the only part of the circuit which has power dissipation. So needless to say, when we want to characterize and understand the resonant frequency, we look at real admittance, which is basically voltage to current, or voltage to that current, which is in phase with voltage, causing power. And another way of looking at your oscillating system, the frequency at which there is the most displacement is obviously the frequency at which you're going to have the most power dissipation, and that, then correlates to real admittance. So at that frequency, so at FR, the real admittance maximum we have our inductor and capacitor canceling out. So what you're going to be left with is just your parallel capacitor and your resistor here. So if we look at our resonant frequency, then, because all of the real admittance is coming from this resistor, the resistor value is actually equal to the impedance at that state. So you just divide that number by the maximum admittance. That gives you your resistor value. In this case, as we see here, the real admittance at the resonant point is 2.48 millisiemens. This is equivalent to 403 ohms. Yep, that's R1. So we got that taken care of. Now we'll go to the second step. So this was C0, and this is R1. What is C0? So at the resonant frequency, so we calculated this resonant frequency. So capacitance in general, if you're looking at the admittance of the capacitance, if you remember, the impedance is according to this formula, where you have your angular frequency and your impedance, your imaginary impedance, which is going to correlate to your capacitance. But keeping things all in terms of admittance, we'll do real imaginary admittance divided by our angular frequency. And the reason that we can do this this transformation is because we have this simple equivalent circuit here. So we go back to our plot. Let's highlight real imaginary admittance on the second column. Let's take us off that. So at the resonant frequency, the imaginary admittance is 470 microsiemens. And the frequency is 38.39, so 38.4 kilohertz. This gives us 12.2 nanofarads. So we have, again, now 12.2 nanofarads, and we have 403 ohms. So we've successfully calculated two of these parameters in the equivalent circuit here. The other point I think I need to mention is the conversion in between. Is a conversion in between impedance and admittance. So if you were to have a spreadsheet of impedance magnitude and phase of impedance, the magnitude of real admittance is equal to 1 over the magnitude of real impedance. The phase of admittance is equal to the opposite of admittance. So it's equal to the opposite of the phase of impedance. Then in order to calculate the real and imaginary values, so for the real component of admittance and the imaginary component, you simply take your magnitude, cosine of the angle, and the magnitude, sine of the angle. Do not use this. This generally is not true. So don't invert the values in order to calculate the other value, because there is complex number mathematics and trigonometry then needing for you to go through this process in order to calculate the values. For example, you can display real admittance very easily on your particular brand of impedance analyzer. Most, if not all, impedance analyzers will have this function to display conductance or real admittance correlating to the power. Again, but you can do but if you do capture the traditional metrics of impedance and phase, this is the method for conversions. So now that we've calculated the parallel capacitance, which is the static or intrinsic capacitance, and the resistor on the LCR circuit, it's time to move to the next step, and that is to calculate the quality factor. The only components remaining are L1 and C1. In order to get these values, we're going to have to combine knowledge of the quality factor of our piezo resonator along with the resonant frequency to then determine exactly what these values are. So let's start by drawing a plot. And here we have our resonant frequency. And at the resonant frequency, it's the maximum real admittance. Now, we can calculate the energy dissipation in an oscillator by calculating its quality factor. And the quality factor basically describes how sharp this resonant peak is. This can also be looked at as a decay factor. Like if you if you apply a step response to your device, how long will those natural decaying oscillations take? Or if it's going to be taking a longer time to decay, that would be a higher quality factor, which has an inherently less damping per energy stored, or the resistor is smaller and the inductor and capacitor have larger values, just storing more energy. So the way we characterize and we describe the sharpness of this peak in order to calculate the non-dimensional quality factor is, and we'll also describe the quality factor more in detail in a few slides down, because it will be one of those summary parameters which are non-dimensional and can be applied and compared across transducer types and is independent from a specific modeling approach. How do we then calculate this quality factor? Well, we use what's called a half power bandwidth. And these, as you probably would guess, do have derivations behind them supporting their relationships. So it's half power bandwidth. So we look for where the real admittance is half the maximum. That's the maximum. This is half the maximum. And this frequency separation compared to the resonant frequency, so we'll call that delta omega, which is a delta of these two values here. Omega r, which is the resonant frequency, divided by the half power bandwidth frequency, as calculated by the real impedance, then gives you directly the quality factor. So if we take a look at our device here, and let's in fact zoom in a little bit. So let's call that 38, and we'll just call this 39, just to get ourselves a little bit closer to that resonance, basically the maximum impedance real admittance, the blue. And I'm basically changing the scale such that I can get, so the maximum real admittance is 2.48, and half of that is 1.25, right? So I'm going to enable the cursor, so they're enabled. So let me just take that measurement again. So I have it all there. I'll take these cursors. Well, this is the anti-resonant cursor. We don't have an anti-resonance right now on the screen. So we'll take cursor 1 and take cursor 2, and as you can see, they are being displayed here, their values. So we want to look for, and this, so cursor 1 is at 1.4 real admittance right here. So we want to take that to 1.25. Approximately there. A little bit higher. Some need for some fine adjustment here. That's pretty good. And down the other way as well. So again, I'm looking for these values here. So you'll try to get them as close as you can. You can do some interpolation if you don't have that exact number. But I think this is pretty good here. We have 37.94. So cursor 1 is at 37.94 kilohertz, and it's at about 1.23 millisiemens. And if you can remember, the resonant admittance was about 2.5 millisiemens. So that's good there. And cursor 2 is at 38.89 kilohertz right there. It's kind of small, so I'll write that out. And it's at about the same value. So you subtract, and the resonant frequency, I think you wrote that down before. The resonant frequency is at 38.4 kilohertz here. So you subtract these two values from each other, and the difference, the delta frequency, is 0.93 kilohertz. So the quality factor is 38.4, which is the resonant frequency, divided by the bandwidth. That gets us to a quality factor of 41. So this is the method and methodology to calculate the quality factor, but it still doesn't directly give us an L or C value. The quality factor, by its definition, is related to 2 pi times the frequency, obviously that's the resonant frequency in this case, multiplied by the energy stored per cycle divided by the power dissipation rate. Through a derivation, you can determine that the quality factor in terms of the LCR circuit is equal to 1 divided by the angular frequency, and that's the resonance angular frequency, times R1 times C1. From this you can isolate C1 as being equal to 1 over omega R times R1 times Q. That gives you a capacitance value of 1 divided by 2 pi multiplied by 38.4 kilohertz multiplied by 403 ohms multiplied by 41, and that has no units. This gives us the capacitance value of 0.25 nanofarads. The next bit of information that we use is the resonant frequency itself, and this is a very well known relationship between a capacitor and an inductor in resonance and their resonant frequency. So this can be used to solve for the inductor, the inductance value, and this gives us 1 divided by 38.4 kilohertz times 2 pi, and that's going to have to be squared multiplied by 0.25 nanofarads. And this here gives us an inductance of 0.068 henries or 68 millihenries. I just need to make a quick correction here, and I'm leaving this in, let's say, because we can all learn from mistakes. When I calculated the capacitance, that is a static or parallel or intrinsic capacitance, we can describe that with many terms. Some are more accurate than others in certain cases. But that discussion aside, the frequency here should be used as an angular frequency, so we really should have a 2 pi factor here. And this then leads to this number become 1.947 nanofarads. Quite a bit different. And I'll describe how I found this mistake, and mistakes are always good. You guys won't forget this now that you've seen me make it. But after, so we calculated all of the equivalent circuit components, and I drew this up in a program called LT-Spice. It's a very simple circuit simulation program, extremely popular. And we see the capacitance, the static capacitance, and also our LCR circuit all represented here. I have a voltage source which I'm going to be driving with 1 volt sinusoidal, so that's sine omega t. I'm going to vary the frequency between 35 and 45 kilohertz. This is in hertz, and using 10,001 points, so I end up with one measurement for each frequency. This resistor here I just have as a point of convenience. It's used to measure current, although this program can directly calculate current without a need for a current sensor. I just put this as a realistic example of perhaps measuring the voltage response and hence being able to measure current going through our piezo resonator. So in this slide here, I'm comparing the calculated impedance versus the measured impedance. So this calculated impedance can be taken from the program, the LT-SPICE program, and that also comes from that equivalent circuit. So I put that equivalent circuit in the program, as you saw, from the parameters that we got. So we took those equivalent circuit parameters, we then modeled them, and then we put them in a circuit simulation program. And again, the equivalent circuit only uses certain characteristics of our circuit, makes assumptions that it does follow, this circuit representation, and we are then comparing that to the measured value, so the actual values measured. We see that first of all that they do match. Actually, when I found that 2 pi error, that I didn't put 2 pi for the angular frequency when calculating the parallel capacitance, the way I found that was this was way off. It did not even match up at all. So that's one kind of a nice thing, is always compare your calculated and measured results, your summary parameter, the result of those parameters in comparison with your measurement. So we have two differences. One of them is insignificant and the other one is actually very significant. The difference here is you see the difference in resonant frequency. Now the minimum impedance, as I mentioned before, it's not exactly the resonant frequency, but they're very closely related. They're approximately an equal distance away from the actual resonant frequency, which is more likely around here. But impedance is a traditional way of plotting this data, so I'm presenting that in this discussion. But I'm trying to say that the resonant frequencies are different. That can be due to two factors. But the major factor is, well, there are approximations done when you are calculating the numbers. So that is with the parallel, so we use many different calculations in order to determine the final equivalent circuit parameters, and due to that factor there's going to be some amount of error propagating through the measurements, and this is actually quite a small, if you were put it in percentage, it'd probably like 0.1% error or something like that, which is insignificant, kind of looking at it from this perspective. But when you sort of put them right on top of each other, well, it starts to make you a little bit suspicious or curious as to why there is a difference. The other is that I remeasured. I didn't save the original data, so I came back when I was making the next part of the recording, and I did a remeasurement. So this type of data does change, a couple of hertz, tens of hertz, from measurement to measurement. So that's another reason why there's a difference. The more significant, I think scientifically significant difference is here, at the anti-resonance frequency. So as you see here from the orange calculated value, it is more sharp, it has a more pronounced peak than the measured value. So the calculated value has a more pronounced peak than the measured value. So this basically says that the accuracy of this model at the anti-resonant frequency, or for this specific transducer, mind you, now it varies between transducers about which part becomes more inaccurate, but at the anti-resonant frequency, there is increased mismatch between the calculated and measured value. So you might think that, hey, the model is not working, but actually the physical system may be nonlinear at this, in its very nature, so you would expect some deviation because we did all of our calculations without using the anti-resonant frequency, as you notice in the equivalent circuit parameters. Now, if we had done our equivalent circuit calculation using anti-resonant frequencies, then we would have found different results. We would have found different set of matching. Perhaps the anti-resonance would have fit better, and the resonance would also fit a little bit worse, so it kind of would get in between. The other thing to note is there's, just like we talked about, a quality factor for the resonant frequency. So in this case, when we use the real admittance, there's also a quality factor A, which is of the anti-resonant frequency, and for that you can use the real impedance. So I'll just draw in this corner real fast. So we had this peak for real impedance, and we will also have a similar peak at the anti-resonance for, sorry, this is real admittance. For real impedance, we'll have a peak at anti-resonance. Now, the sharpness of this peak is obviously different between these two simulations, between the measured and simulated values, based off of parameters calculated from the resonant frequency. So there are physical differences, likely in the damping factor. So if you had changes this resistor, you would likely fit the calculated and measured value more accurately, but there are here, as clearly shown, physical differences in the damping factors in these two situations. So just note that there's going to be discrepancies, and those discrepancies can be insightful, but for example, for devices where you're mainly concerned about resonant frequency, you would opt toward using parameters measured there versus resonance and anti-resonance. But plotting your data on top of each other, calculating measured value, if you have accuracy where there is a need for where you're operating your device, that's the best approach. So in summary, the equivalent circuit matches very well, but there are differences. There are different ways to calculate the equivalent circuit rather than what I've just explained, and you will have a trade-off between the parameters you choose to use and the ease of measurement and their accuracy. There are also other methods of determining the equivalent circuit rather than what I just mentioned. So again, we have 1, 2, 3, 4 components, so we'll need 4 unique measurements. Some of them you'll have to combine the measurements for to calculate values, and some of them independently. For example, the resonant frequency independently will be able to get you the resistance here, for example. So there's other ways to calculate the off-resonance impedance. So there are other ways to calculate the equivalent circuit. One of the ways is to use the off-resonance impedance or admittance to calculate the total capacitance. So at off-resonance, these two parameters drop out technically. So this is what you measure. This is what actually occurs. So you can use this equation here. You can measure your capacitance at off-resonance. You can just use this equation as one of your equations that you use to solve. You can also use the anti-resonant frequency to calculate the static capacitance. So the anti-resonant frequency and can be used in certain ratios to also be included in determining your capacitance values. There are also alternate equivalent circuit. One of them, namely what's called the Mason's equivalent circuit, uses transformers to describe the electromechanical coupling. You can also use an anti-resonant focused circuit, which instead of having an LCR circuit in parallel with a capacitor, that circuit, highlighting the anti-resonance operation, has a parallel LCR circuit in series with a capacitor, and that can be used if you are focused on using anti-resonance analysis, especially if that's the primary mode of operation of your final device. It may be useful to describe your system in those terms. Now we'll jump in here